Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. Assalamu alaikum, everyone. So let's solve recitation problems for chapter 14 about fluids. So first of all, let me remind you about what we did in class, the main important relationship. Okay, first we talked about hydrostatic pressure. P at a certain height or at a certain depth inside my water. Let's say this is water. This is P0, the pressure here. Okay, this is at depth H. What the pressure at depth H due to water? Pressure at depth H is equal to P0 plus rho dH. Okay, pressure increases with the depth H. That's number one. Now, we talked about a buoyant force. So the buoyant force, you know the direction is upward. What's the magnitude of the buoyant force? Is mfg. It's the weight of the fluid, of the displaced fluid. Okay. Now, if you remember correctly, what is mf? Mass of the displaced fluid. It will be the density of fluid multiplied by the volume of the fluid which is displaced. Now you remember what is the volume of fluid displaced? Well, the volume of fluid which is displaced, Vf, is a percentage of the volume of the object. So basically it's equal to the volume of the object if the object is totally submerged. Okay, 100% submerged, of course. Okay. If otherwise, it will be just a percentage of the volume of the object, you know. So basically, the percentage of the volume of the object which is submerged, basically. Okay, good. Now, floating. We said if the object is floating, displacing its own weight. When I have floating, I have buoyant force is equal to gravitational force of the object, meaning mfg will be equal to mg, m being the mass of the object. Okay, mf is equal to m. That means rho fvf is equal to rho object v object. Okay. And then we talked about if I have an object which is inside water and I put a scale here. Okay, so I have, let's say this is the tension, it's the reading. This is the gravitational force. And of course, this will be the buoyant force. So the tension will be the apparent weight. Tension is apparent weight. Apparent weight will be equal to what? Real weight, actual weight, which is mg, gravitational force, minus buoyant force. Apparent weight is equal to actual weight minus buoyant force. Okay? And buoyant force, you already know how to calculate it. Okay, so now let's go and then we solve our problems. This is the first problem. We have a small sphere made of a material of bulk modulus. This, Pascal. The volume of the sphere shrinks by 0.20% when submerged in a fluid at a depth 400 meters. What is the density of fluid? Assume that the pressure on the sphere at this depth is the same from all directions. Okay? This is very important because I want to have a uniform compression. Okay, so the pressure of the sphere at this depth is the same for all directions. So you will have a uniform compression. Okay, and this is justified because the height is very deep. That's the first thing. because also the sphere is small. Okay, this is why I said small sphere. Good. So you know that hydraulic pressure F divided by A is equal to bulk modulus delta V divided by V. Okay. So delta V divided by V is what I gave you. So this is equal to 0.20%. Okay. So F divided by A is what we call hydraulic pressure, okay, or uniform stress, right? Uniform compression. So it's a pressure. This is equal to P. But P at a certain depth H. Okay. So you remember that P at a certain depth H is equal to P0 plus rho GH. And this is equal to what? P delta V divided by V. Again, this delta V divided by V is equal to 0.20%, as we said, and it's only due to the height, okay, to the depth of water. So basically, this does not play a role here, the P naught. Get my point? Okay, because before my small sphere was in air and the atmospheric pressure already, did it work already? Okay. So this shrink of 0.20% is not due to the atmospheric pressure. It's just due to the rho GH. Okay. Good. So the density will be B delta V divided by V divided by GH. And you calculate it and you get your answer. So, and you get your answer. Okay. So in this problem here, I have a floating problem. I have a block of wood which float in fresh water with 2/3 of its volume submerged, and with 0.90 of its volume submerged in oil. Okay. Find the density of the wood and find the density of oil. So as we said, floating, buoyant force is equal to gravitational force. Okay. So you simplify by G because buoyant force is mfg, this is m, so basically you get m. F is equal to m. So what is mf? That is a mass of the fluid displaced. Okay, so mf will be rho f vf, the volume of the fluid which is displaced, which is equal to the mass of the object, basically. The mass of the object will be rho v. Okay. Now, in fresh water, you will have raw water multiplied by the volume of the fluid which is displaced. So you have to look at the volume of the object which is submerged. So it's 2/3 of V. V being what? V being the volume of the object. And this is equal to rho object, let's say wood, multiplied by V. So this V goes away. So rho, which is the density of the wood, is just 2/3 of the density of water. Okay? And you know what the density of water is? 1,000 kilogram per meter cube, or a gram per centimeter cube. which is also a kilogram per liter. Okay. Now, in oil, what do I have? I have the same thing. Basically, raw oil multiplied by the volume of oil which is displaced, which is 9 divided by 10 volume of the object, is equal to what? Raw of wood multiplied by the volume of wood. Okay, so you see that the V goes away. So raw oil will be just 10 divided by 9 multiplied by the raw of my object, which is 2 divided by 3, which multiplied by raw of water. And you get the raw of oil. So this is what we get for the raw of oil, of course, and this is what we get for the raw of wood. Let's go to the next problem. So we have a rock of mass 5 kilogram of density for 10 to the power 3 kilogram per meter cube. Okay, so I'm giving you basically the volume. Okay, rho is mass divided by volume. Volume is mass divided by rho. So the mass of the object will be what? 5 divided by 4.8 10 to the power 3. And you get the volume of the object. So this object is suspended in water by a string, such that a half of the volume of the rock is inside water. What is the tension in the spring? Okay. So the tension in the spring is the apparent weight. You know that you have an equilibrium problem. Okay. Okay. Floating is an equilibrium problem. That's why gravitational force is equal to buoyant force. This is not floating because this is the object is much denser than water. So normally it should sink. But now I am suspending it using a string. Okay. So the tension in the string is going upward. Okay. And of course, buoyant force is going upward. And of course, gravitational force is going downward. So you know that the apparent weight by balance of forces, apparent weight tension, is equal to gravitational force mg minus buoyant force fb. Now, of course, what is a buoyant force? So let's write it down. So this will give us mg minus mfg, right? Okay. Now let's write what is mf. Mf is rho f vf, which is rho f. What is the volume of fluid which is displaced? It's half the volume of water, the volume of the rock, because only half of the volume of the rock is inside water. So half volume of the rock. Okay. So this is what we did here. So this is gravitational force, mass of a rock g, and this is the density. This is a buoyant force. Okay. Rho water, this is rho f, multiplied by volume vf, which is half volume of the rock. And then multiplied by g, of course. So you work it out and you get the tension is equal to this. Okay. Apparent weight is equal to real weight minus buoyant force. And buoyant force is equal to mfg. So here it's just rho f, which is water, vfg. So it will be rho f, which is water, vf, you know, it's half v, v being the volume of the object multiplied by g, and it gives you this, and then you get your answer. So I can skip this problem as well because, solution is given and it's the same. Okay, here it floats this. Okay. No major difficulty here. I have a certain block of wood. It has a certain volume and it floats when 25% of its volume is submerged in water. Okay, it floats in water with only 25% of its volume submerged. So floating, as we said, MF is equal to M. Okay, when I float, I displace my own weight of fluid. So that means rho F VF is equal to what? Rho object V object. Okay, good. So here, rho F is rho of water, of course. V of the fluid displaced is 20% of the volume of the object. And this is equal to what? Rho of the block of wood multiplied by V, which is the volume of the block of wood. Okay. So by this, you know that the density of this block of wood. Okay. So the density of the block of wood is 25% of the density of water. Now, what is a downward force what is a downward force that must be applied in order to hold the box underwater? Okay, so if I hold the box of wood, the block of wood underwater, so I apply a force downward here. Okay. Of course, I will have the gravitational force, which is also downward, but also I will have the buoyant force, which is upward. Okay, so here I will have what? Buoyant force minus the force that I apply downward here, okay, minus gravitational force is equal to 0. So that means that the force that I apply is just equal to what? Buoyant force minus gravitational force. Okay. Now we already calculated what is a buoyant force. When I am fully submerged, because I want to hold the box underwater. So it will be MFG minus MG. And MF is equal to what? It will be equal to rho F VF. But VF here will be equal to V of the object because everything is inside. Okay. Minus mg. That is m, it will be rho of the object multiplied by the volume of the object multiplied by g, of course. And here, I forgot the g here. So what will I have? I will have rho water, rho of the fluid, multiplied by the volume of the object multiplied by g, minus rho of the object, which is 0.25, multiplied by rho water, multiplied by the same volume of the object, multiplied by g, because now everything is here. So this will give me what? 0.75 rho water, volume of the object, multiplied by g. So this is the solution here, as we said. Okay, 0.75 rho water, volume of the object multiplied by g. Of course, the volume of the object, I have to transform it. I have to put it in the right units. And I put everything in the right units, I get 1.1 Newton. Okay, let's solve this problem as well, which is very important. Okay, I think I will skip this problem maybe. Let's go to this one. What do we have? We have an object which is hanging from a spring balance when submerged in water. The object weighs 1/2 of its weight in air. When submerged in a fluid of unknown density, it weighs 3/4 of its weight in air. What is the density of the unknown fluid? Okay, so here, of course, when I submerge the object in water, I mean fully submerged, because the object will sink. Okay, so when I say submerge it in water and I give you the weight, I'm telling you that the object is fully submerged in water. In fluid as well, it's fully submerged in the fluid. Okay, so in reality, the object is denser than water and denser than the fluid with unknown density. Okay, good. Now, we will use, again, apparent weight is equal to real weight minus buoyant force. Okay, so apparent weight, I'll call it W up, for instance. Okay, so in air, what's the apparent weight? The apparent weight is half of the weight in air. Okay, so let's say half of weight in air, I will call it W. But this is equal to what? This is equal to mg minus the buoyant force. So I mean it's fully submerged. So the buoyant force will be mfg. So it will be rho f, rho water. So because at the beginning I'm talking about water, right? So rho water multiplied by the volume of the object, because Vf will be equal to V, which is the volume of the object multiplied by G. So this is in water. Okay. In fluid, in the other fluid, W apparent weight is 3/4 of W, which is equal to what? Which is equal to mg minus mfg. So it will be what? Rho of the fluid that I don't know. This is the density that I want, multiplied by the volume of my object, multiplied by G, because the object is fully submerged. Okay, good. By the way, in air, you know that mg will be equal to the weight. Okay. By the way, in air, you have buoyant force, but this buoyant force is negligible compared to the buoyant force inside water, of course. So this is what you get. So as I said, weight in air is W and it's mg. So basically I have this weight mg minus this, and this is half of the weight because I'm in water. I have the same weight, which is mg minus buoyant force is equal to 3/4 of the weight in air. Okay, so bottom line, I can write this. Okay, I can write this density as terms of weight in air. And then I take the ratio. If I take the ratio, I will find that the rho x is half of the rho water. Okay, so I am solving a lot of problems about this, but they're important. So here we have an object of density 7.9 gram per centimeter cube. So you know that it will be 7,900 kilogram per meter cube in SI units. Now hangs from a balance. And this density, of course, is equal to the mass of the object divided by the volume of the object. So the balance read 80 Newton when the object is in air, right? And 71 Newton when it's completely immersed in a liquid. What is the density of the liquid? Good. So the balance reads this 80 Newton when the object is in the air. So you know that in the air, I can neglect the buoyant force. So basically in the air, the reading that I will call T, tension, is equal to 80 Newton. okay, in A. The A is 80 Newton. So this will be equal to mass of the object multiplied by G. So that means I know what is the mass of the object. Mass of the object will be 80 divided by 9.8. And I have it in kilogram. Now, since I know the mass of the object, I know the volume of the object because I know the density is rho V. So that means the volume of the object, let me just calculate it, will be equal to what? Mass of the object, 80 divided by 9.8 divided by rho, okay? So 1 over rho, which is 7,900. Okay, this is the volume of the object, just in case I need it, in meter cube, of course. Now, when I'm in water, the apparent weight is this. So in water, you know that 71 Newton will be equal into the real weight, which is 80, okay, minus the density, minus the buoyant force, basically, okay, FB, okay. So you know this. Apparent weight is equal to real weight minus buoyant force. That means that the buoyant force is equal to what? 9 Newton. Now, what is a buoyant force? Of course, it will be mfg. So what is mf? As you know, mf is rho f vf g. Okay, and this is equal to 9 Newton. Okay, and what is vf? Rho of the fluid, v of the fluid. Well, v of the fluid, you know that it's completely immersed. So it will be the v of the object. Okay, the v that I calculated here. The v g is equal to 9 Newton. So that means that rho of the fluid will be equal to 9 divided by the volume. So what's the volume? We already calculated it. It is this 89.8. And then I have here, okay, of course. And then I have here 9.8. Okay, good. So 9.8 goes away. So you get the volume of your fluid in kilogram per meter cube. So how much do you get? So it gives you what? 890 kilogram per meter cube, which is 0.89 gram per centimeter cube. Okay, good. Let's go to the next one, which is about Pascal principle. So the figure below is showing us the schematic of a hydraulic lift. The right piston in a hydraulic lift has an area A, capital A, which is 3 times the area of the left piston. Okay, this is small a here, this cross-sectional area here. When the pressure at the smaller piston is increased by delta P, then the pressure in the larger piston is also increased by delta P. Okay, because pressure is transmitted through the incompressible fluid, is integrally transmitted. Okay, so same change in pressure. So if I change the pressure here, delta P, each portion of my incompressible fluid will change its pressure by delta P. So of course, A is the correct answer. Now the force here. So you know that delta P A will be equal to delta P capital A, which is delta P. And you know that delta P is, if I have here this force, small force, it will be F divided by A. Now on the output, I will have a capital force, of course. So it will be capital F divided by capital A. Okay, the change in pressure is the same, but the force will be multiplied 3 times because A divided by A multiplied by small a. And this ratio here is 3. Okay, good. So be careful, depending on the problem, of course, the change in pressure is the same, but the force is multiplied. And I can tell you what's the change in volume. Of course, the change in volume will be the same. What's this vertical distance here? And I already discussed this in class. Now let's look at this problem here. I want to lift this car. And this car has this weight, W. Okay, so hydraulic press again. I give you this cross-sectional area by giving you R1, the radius, and I give you this force here, F1. Now the question is, what should be the radius here on the right and larger piston in order to lift this car? So in order to lift this car, I have to apply here a force F2, which is at least equal to the weight here. And then I will say that the change in pressure is the same. Of course, you will have F1 divided by this cross-sectional area, which is pi R1 square, should be equal to the pressure here, which will be the weight at least, okay, divided by pi R2. And of course, this weight, F2, should be at least equal to this weight or bigger. Okay, so that's it. So my only unknown, so here F2 will be the weight, of course. My only unknown will be R2, and then R2 should be this. This problem is also very interesting. We solve it in class, so I'll let you look at it. Basically, you can solve it 2 ways. Either you look at the pressure here of the liquid here is equal to the pressure at the same height here, okay, like in the lecture. Okay. The shortcut is to say that the weight of this cylinder here is equal to the weight of this column of liquid. Okay. So the weight of this is equal to what? Will be equal to mg divided by A, but in reality, T1. So what is the weight here? Of course, it will be what? Okay, so what is the weight here? It will be the mass of the cylinder multiplied by G. What is the weight of this column of water or this column of liquid here? Of course, it will be mass of this column of liquid multiplied by G. Now, what is the mass here? It will be the density of water multiplied by the volume, and the volume will be this cross-sectional area A multiplied by this change in height. Okay, so I will have the weight of the column of water will be density of water multiplied by cross-sectional area multiplied by the HL, this height here, which is HL minus HR. Then multiply by G. Of course, the G will simplify. So you have M, which is just raw water, cross-sectional area, change in height, HL minus HR. And you do that and you find 1.5 kilogram. Okay, let's go now to this problem here. So here we have 4 arrangements of pipes, as you can see, in which water flows mostly towards the right. So I give you the different radii of pipe sections. So the question is, when or which arrangements is the net work done on a unit volume of water moving from the leftmost to the rightmost section is the greatest? Okay, so here I will use Bernoulli equation. And you know that Bernoulli equation is coming from conservation of mechanical energy. So when I use Bernoulli equation, you have horizontal pipes. So this part here of the Bernoulli equation cancels. There is no change in gravitational potential energy per unit volume. So I will just end up with P1 minus P2, okay, is equal to half rho V2 square minus V1 square. Okay, so this I will call it 2, this I will call it 1. I mean, input is 1, output is 2. So this is representing what? The network done per unit volume. Okay, the network done per unit volume, because I told you if I multiply by volume here, I will just get work applied is equal to change in kinetic energy here. So here change in gravitational potential energy is 0. If I just take this equation here and I multiply by the volume, that's what I will get. I will get this. Okay, so the network is just the change in pressure. Okay, and it's equal to half V2 squared minus V1 squared. So the question is, which one has the greatest network? Basically, on which of these 4 configurations do I have V2 much larger than V1? So of course, you know that I have to use A2 V2 is equal to A1 V1. Continuity equation. Okay, because of course water is an ideal fluid and it's moving here. Ideal fluid in motion. I will use continuity equation and Bernoulli equation if I have an ideal fluid in motion. Ideal means 4 things, right? Steady motion. Second, non-viscous fluid. Third, irrotational fluid. So no turbulence. You have a laminar fluid, what we call a laminar fluid. And fourth, what's the fourth? Who remembers? I forgot. Okay, so I said steady fluid, irrotational, of course, incompressible. Okay, that's a very important, incompressible. So non-viscous, incompressible fluid, irrotational, and steady state, steady motion. So here, obviously, number 2 will give me the largest. Okay, because you see here, I'm going from a large cross-sectional area to a small cross-sectional area. So the difference between, because of this case of V2 here, will be larger, okay, than V1. And you know the ratio, because this is 3R and this is basically R. So the cross-sectional area will be pi R square. Here the cross-sectional area will be what? Pi 3R square. Okay. So 2 will be the largest. Of course, here, well, they will be equal because this cross-sectional area equal to this. Here also they will be equal. Here you can see that it will be even smaller. Here the V here will be larger than the V here. Okay. But 2 obviously will be the right one. Good. So read this question carefully, and then I will solve it. So the first question is, find the magnitude of the frictional force between the plug and the pipe. I want the frictional force here. Because normally, because of this water, well, the water is pushing. The water is exerting a pressure on the plug, and the plug should move. But because there is friction between the plug and the edges here, it will be closed. So let's do a free body diagram and apply Newton's second law. So I have an equilibrium problem. So my system here is a plug. So outside the plug, you will have atmospheric pressure. So atmospheric pressure is pushing. So you will have the force, which is P naught multiplied by A, pushing inward. On the other side here, you will have what? You will have the pressure of water here, pH, multiplied by cross-sectional area, because you remember that force divided by A is, of course, pressure. So this is pushing my object towards the right. Okay. And of course, you will have frictional force, which is opposing This frictional force will be like this, because obviously this is bigger than this, and frictional force will be opposite to the pushing of the water. Okay, so what will you have here? I will have balance of forces. So pressure at the depth multiplied by cross-sectional area is equal to atmospheric pressure, right, plus frictional force. So this is what I have here. So that means frictional force, well, the atmospheric pressure will just cancel, because you remember that pressure at this depth here is pH, is P0 plus rho GH, and here H is equal to D, small d. Okay, yes. So atmospheric pressure will cancel, okay, because the atmospheric pressure is pushing here, but it's also pushing here, right? So this and this will cancel. So basically my frictional force has to just counterbalance the hydrostatic pressure. So the frictional force F should be equal to the hydrostatic pressure, which is rho G D. Multiply, this is the pressure, multiply, of course, by the cross-sectional area. Okay, so frictional force will be rho water, because it's water, G 9.8 multiplied by D. D is this depth, and it's given, it's equal to 6 meters. Multiplied by the cross-sectional area, and the cross-sectional area here is a kind of cylindrical cross-sectional area. I gave you the diameter, of course. So you can use pi r square, and the diameter is given 4 centimeters. So that means the radius is 2 centimeters. Of course, you put everything in SI units and you get the friction is 74 Newton. Now, what's the second question? The second question is, when I remove the plug, what is the volume? What is the water exiting the pipe in 3 hours? What is the volume of water exiting the pipe in 3 hours? First, I have to find what is the speed of the water exiting. So at which rate the water is getting out. Okay, what's the volume of water getting out per unit time? So I will apply Bernoulli equation between the top here and here, this depth here. So I will have P1 plus rho water V1 square plus rho GY1, okay, is equal to what? P2 plus half rho V2 square plus rho GY2. V2 is basically 2 is this position, okay? So 1 is here and 2 is this position when the water is getting out, okay? Good. Now, of course, this is a dam. So this is extremely large. I mean, it's semi-infinite. So I will say that continuity equation, of course. Cross-sectional area of this surface here, the surface of water, multiplied by V1 is equal to cross-sectional area of the plug multiplied by V2. Since this is almost infinite, of course, this V1 is almost 0. So that's why this V1 will be 0 here. P1 will be atmospheric pressure because it's in contact with water. P2 will be atmospheric pressure because it's in contact with water, so they will cancel each other. So at the end of the day, you will get the famous this, and we did this in class already with the tank and the desperados who fired at the tank. Basically, we have that V2 is equal to square root of 2GH, and H here is D. Okay. And we get V2. Now we can go back to our volume flow rate, okay, is AV, okay, A being the cross-sectional area of the pipe. So, and then we multiply by 3 hours to get how many meter cube is getting out in 3 hours. Okay, good. Now here also we will use Bernoulli equation and continuity equation. Okay. So I will apply Bernoulli equation between 1 and 2 here. Okay. In the same streamline. P1 plus half rho V1 square plus rho GY1 is equal to P2 plus half rho, of course here there is a rho, it's forgotten. Okay, V2 square plus rho GY2. So I know the Y's, I know the, do I know the V's? Not yet, but I can get them. Okay, so the question is to get P2, of course. So P2 is equal to this. And be careful because here I'm talking about gauge pressure. But if I do P1 minus P naught, well, P2 minus P naught as well. So, okay, I can also talk about absolute pressure because gauge pressure is, you know, the change in pressure with respect to the atmospheric pressure. Okay, so we get this from the Bernoulli equation. Of course, I know this guy here. I know this. I know, of course, rho, it's water. I know V1. So the question is, what is V2? How to get V2? Once I get V2, I get P2. So to get V2, I use the sister equation of the Bernoulli equation, which is continuity equation. Okay, and then I get V2. Once I get V2, I plug everything and I get my answer. Okay, put everything in SI units and you find 4.6 kilopascal. Let's come to this problem now, and I will discuss a little bit about physics here. Read the problem carefully and inshallah, let's solve it. So the problem reads, a large open tank filled with water, large open tank filled with water has two holes, small holes, and this is very important, large, small holes. On its bottom, one is twice the radius of the other. So this radius here is twice the radius here. In steady flow, I'm putting you in condition of what? Ideal fluid in motion, steady flow, non-viscous, irrotational, incompressible. What is the ratio of the speed of water leaving the larger hole to the speed of water leaving the smaller hole? Okay, good. So the speed here, V1 with respect to V2, are they equal? You know, is it, you have a ratio less or more than 1? We will see. But again, this is very important, large hole and small hole. So of course, this is open. So here I have atmospheric pressure, P naught. Okay. And this is large, this cross-sectional area here of the tank, I will call it A naught. It's a contact with atmospheric pressure, so it will be P naught. Okay. Now here, let's say that at this is height H. So here you have a difference of height H. Okay, good. So these two holes are at the same height from the top of the surface of the water. Good. Now, what I will do is I will apply Bernoulli equation between here, 0 and 2, and then 0 and 1. So let's consider a streamline doing like this, and another streamline doing like this, and I will apply Bernoulli equation. So Bernoulli equation will give me P naught plus half rho water V naught square plus rho G H is equal to what? Let's say P1 first. P1 plus half rho water V1 square plus rho G 0. Okay. So now if I apply Bernoulli equation between 0 and 2, I will have P1 plus half rho V1. Between 0 and 2, P2 plus half rho V2 square plus rho G0. Okay. Now, let me apply now continuity equation. But again, between the surface of the water and V1 and V2. Okay, surface of the water and the holes. So I will have A naught V naught is equal to what? A1 V1, which is equal to A2 V2. Okay. So that means what? Of course, this is very large and this is very small. That's why I said these are small. Okay, that means the velocity is very large, the velocity is very large, meaning what? Meaning basically V0 is very small compared to V1. V0 is very small compared to V2, meaning this I can disregard it. The velocity of water, the speed of water here is roughly 0. Okay, good. Now, what the pressure here, P1, of course, it's getting out, it's in contact with the atmosphere. So P1 is equal to 0, P2 is equal to 0. Okay, I mean P0, which is atmospheric pressure. So P1, this is equal to P0, and P2 is equal to P0. So I end up with what? Rho GH is equal to half rho V1 square, which is half rho V2 square. That gives me what? V1 is equal to V2 is equal to square root of 2GH. And this is extremely important, and we demonstrate this in class already. Basically, it looks like water free falling from a height h. I drop water from initial speed at rest. Okay, V0 is equal to 0, and I drop it at this certain height. This is the velocity of water when I, fall freely from rest at a height h. Okay, V here, V final here, as you know, is square root of 2GH. Okay, so that's the speed. So basically they are equal. V1 is equal to V2. So physically, what do I have? Well, I'm just transforming a hydrostatic pressure into a kinetic energy. Okay, so I'm transforming rho GH into half rho V square. And this gives me this. Okay, now a student came to me and brought me this problem. He asked me a very good question. He said, why we did not apply basically continuity equation between hole 1 and hole 2. Because when you do that, you will see that, since the one radius is 2 times the second radius, one surface area is 4 times the second one. Okay? Okay. But here, what you need to realize is the motion of water here and motion of water here are both linked to the height, the hydrostatic pressure. I build the height with water. I'm not basically, if I close it here, for instance, and I'm pushing in one hole and it's getting out from the other hole, I can apply this continuity equation between the two holes. But here, I'm not directly applying the continuity equation because, both of them are connected to the hydrostatic pressure, which is being transformed into a kinetic energy. Okay. So it's not I'm pushing in one hole and it's getting out in another hole. No. Okay. Good. So actually this speed here is irrelevant, is independent of the area of the hole. As long as the tank is very large, okay, the speed is the same, roughly, because this V0 will be very small compared to this V, the speed of the water at the hole. Good. And this is known as the Torricelli law. Let me remove this and then I will show you this. This is a Torricelli law. It's known since, I believe, the 17th century, okay? 18th, 17th century, I think, yes. So you have the Torricelli law. Okay, I have a reservoir full of water. I put different holes at different heights. And you see that they are getting out of my reservoir in a projectile motion, in a sense. Okay? So they are going out of the reservoir in a projectile motion. Okay? And of course, the lower hole will have the strongest jet, as you can see it. Okay? And this one has a, projectile motion, and of course the range is smaller. So the speed of the water getting out at a certain height is just 2 square root of 2gh. That means here, for instance, if I put this upward, when the water gets out, it will get out with the speed of square root of 2gh, and it will go up, 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 up at the same height, and then fall down again. Okay, good. So here, the speed is independent of the cross-sectional area of the holes. Okay. I'm just transforming the hydrostatic pressure into a dynamic pressure. Okay. Good. Torricelli law. It's written this. Check it out. Now let's look at this problem. Water is poured into a very large open tank, again, at a volume flow rate Q, as you see in this figure. So the tank has an opening at the bottom. The area of this opening, let me call it A, small a, is the cross-sectional area of this opening. So the area of this opening for the water level in the tank to be maintained at a fixed height h is. Okay. So here, of course, I will use the continuity equation. What get inside the tank, get outside the tank. You know, the volume that get in per unit time is equal to the volume that is getting out per unit time, because this h here, I want it to be constant. So that means I am adding this volume per unit time. So what is getting out is a volume flow rate, RV, here. This is equal to 0. Okay. The water which is getting in per second is equal to the water that is getting out from my tank per second for this hole. So I will end up with plus Q is equal to A multiplied by V, because you remember RV is cross-sectional area of the hole multiplied by the speed of water at that hole. Now, what is the speed of water? Continuity equation, RV. Okay. So what is the speed of water? Of course, I will use a Bernoulli equation. Okay, Bernoulli equation. Here I have atmospheric pressure, of course, P0, and here I have atmospheric pressure as well. Okay, so I will use Bernoulli equation between this 0 and 1 here. So you will have P1 plus half rho V1 square plus rho G0 is equal to P0 plus half rho V0 square plus rho G capital H. Okay. Of course, P1 is equal to P0. Both of them are atmospheric pressure. Okay. Now this is 0, of course. Now V0, of course, this is a large. So by volume flow rate, you know that the volume flow rate is constant, is small a multiplied by V, but it's also equal to capital A being the cross-sectional area of the large tank multiplied by V naught. Since this is very large, this is very small. Basically, I'm just saying, as I said, V naught is very, very close to 0. In other words, V naught is very small compared to V. V being the speed here. Okay. So I can neglect V naught. So I end up with basically V1, which is V is equal to just square root of 2G capital H. Now let me come back here and plug it here. So I will end up with A. So this equation give me A is equal to plus Q divided by V, which is plus Q divided by square root of 2GH. So the first answer. Okay. So there are many other problems. I want you to solve them all, understand them all. But if you realize these things is coming again and again and again, if here, for instance, you will use in tandem the Bernoulli equation between A and B. Of course, I'll give you everything. Only one unknown, B2. B2 is unknown. Of course, you will use also continuity equation. So solve it. You know, here, this is another problem. Instead of opening it, now here I have pressure of free atmosphere, 3 times atmospheric pressure. So And of course, here I will have atmospheric pressure. So this will be 3 minus 1. So basically 2 atmosphere. I put it in, of course, Pascal, and to the power 5 multiplied by 1.01. And you solve it, okay? So you get my point. You can solve as much as you want. Understanding beats, of course, quantity. Quality always beats quantity, okay? So this is a projectile motion, as I told you. When it gets out, it's a projectile. As you can see, it's getting out of the water. And here I ask you, what is the height? Okay. Good. All these are all the exams problem. Please solve them another